I'm going to talk to you about some trickiness that you need to consider when working with residues in Laurent series. So it involves a radii of convergence. So I should tell you where I'm integrating these. Z equals 4, and how about z equals 1? So I'm going to integrate 1 over sine z dz around this circle, and I'm going to do it incorrectly. And I'm going to do it incorrectly by saying, oh, sine z equals z minus z cubed over 3 factorial plus da da da. Oh, equals, I can factor out a z times 1 minus z squared over 3 factorial plus da da da. Oh, and this is a 0, a multiplicity 1, so I can use that theorem that we saw earlier. So the residue at z equals 0 equals 1 over sine z, but you take the derivative of the bottom, you evaluate the top at z equals 0, you evaluate the bottom at z equals 0, and you're left with 1 over cosine z evaluated at z equals 0. Oh, that gives you just 1. So the answer is 2 pi I times 1. And I'm saying that that is, at the very least, incorrect reasoning. The reason why is if you draw a picture, you get a circle of radius 4 is what you're integrating over. If you think about this for a second, sine z is going to have several singularities there, at 0, at pi, and at negative pi. And so what you really need to do is you need to find the Laurent series for this entire integrand at all these 3 different points. So we kind of tried to get out of figuring out what the Laurent series was by using this theorem, which is perfectly fine, but we just need to know, we need to use some common sense to figure out exactly what the problem entails. So in fact, if you actually figured out the Laurent series centered around 0, you would get that this would be the residue, but you would get that that the region of convergence doesn't hit pi or negative pi. You'd have to use a different Laurent series which doesn't involve this thing for those. So that's the problem with this logic. So let's look at this more complicated problem over here, which will have a happier ending. F of z is defined to be this power series over the entire integers, so this is Laurent series, 1 over 7 to the n, z minus 3 to the n. And I'm just going to take it, the integral over z equals 1. Well, let's see. As a circle of radius 1. So here's some reasoning, which is maybe this is going to be incorrect. It's going to give us the right answer, but it's going to be incorrect. So here we go. This Laurent series, look, you can plug in any number into this Laurent series, and it's going to work out, except for z equals 3. So the only bad point here is at z equals 3, and that isn't included in our circle. So the answer is going to be 0 by Cauchy's theorem. Okay, so this is incorrect reasoning. Here is correct reasoning. It's the right answer, it's just incorrect reasoning. The right answer is the region of convergence, if you use the ratio test, say, is 7. So if you use the ratio test, you get that this converges for a region of 7, except, of course, you can't actually have it converge at 3. So it's actually an annulus, but it goes up to 7 away. So the region of convergence actually looks something like this. It goes to negative 4. You're not allowed to use that point. So it's a little annulus like that. But notice that the thing we care about is completely contained in there, which means this power series, this Laurent series, actually is valid everywhere inside here. So you can actually use this Laurent series here, and now you can say, oh, well, the function's holomorphic over here, so the integral is 0. So now you can have this equals 0 by Cauchy's theorem. But notice you could not use that logic if you want to integrate around, say, a circle over here. Over here, this function, this Laurent series here, tells you nothing about what happens over in the third quadrant here. So you'd have to try something else. Thanks. Bye-bye.